I will talk about hardware distortion correlation in the uplink of massive MIMO systems. And I am Emil Björnson. I'm an associate professor at Linköping University and a visiting professor at KTH. And this is based on joint work with Lucas Anginetti and Jacob Hoydis. So this is going to be about Massive MIMO. And what is Massive MIMO? Well, that is the latest physical layer technology for the cellular networks, sort of 5G networks. And the idea is that you have a base station with many antennas, say 64 or larger. And you use these antennas to steer beams to users, both in the uplink from the users to the base station and in the downlink from the base station to the user. And by having directional transmissions to the users, you're able to serve many users at the same time. So I would say that a massive MIMO system should support at least 8 users at the same time and frequency in different angular directions. And what makes it massive is the antenna ratio, M divided by K. So M is the number of antennas, larger than 64, for example. K is the number of users, say larger than 8. And the ratio M divided by K is something that is greater than 1 or much greater than 1. In this case, it's 8, for example. And what this talk is going to be about is something that we call hardware distortion. And we focus on the uplink. And at every antenna that is receiving the signal from the users, what will happen is that you get an input signal, and then it goes into the hardware. There is a low noise amplifier, an LNA, that is amplifying it. There is an IQ mixer that is separating the in-phase and the quadrature components. And there is an ADC, an analog to digital converters, that takes the analog signal and turns it into something that is now a digital signal. And all of these components are creating different kinds of distortion. There are non-linearities in the LNA. There can be imbalances in the mixer, and there is definitely always quantization noise or quantization distortion in the ADC. And this type of non-ideal base station hardware is something that we often neglect when analyzing massive MIMO systems. But in this talk, we will focus particularly on these things. So let me provide a background about this. So the received signal at the M antennas is coming from these different users. And the reason to have multiple antennas is that you receive multiple copies of the same signals. They are correlated with each other. They're not entirely the same because they contain the signals going over different channels to the base station antennas, but they're still correlated. And that also results in that the distortion at the different antennas is also going to be correlated. And this correlation is often neglected in literature. I have written a book called Massive MIMO Networks, for example, where we neglect something like this. And I have been claiming that those kinds of results are still fairly accurate, but recently there are a number of papers that are saying that these approximations are physically inaccurate, which they definitely are. The question is if this have a large impact on the end results. Because all models are wrong, but the question is which models are accurate enough in order to give us accurate enough results. So in this talk, I will show you that in a massive MIMO system, these approximations where we neglect distortion, that correlation between different antennas, is something that we can do and it have a small impact. So we are considering an uplink system. As you see here, we have M antennas at the base station. We have K users, user 1, 2, lowercase k, and capital K here. And each one is sending a signal, S1, S2, SK, S capital K. And these are complex Gaussian signals, and they have a power P. This is a typical type of assumption. And each of them is traveling over a narrowband channel to the base station, represented by a vector, H1, H2, HK. And this vector of length M is describing the channel from the user to each of the M different antennas. And these are typically different for different users because they are located at different locations. And the received signal at the M antenna inputs here, which is still something that is analog, is going to be modeled like this. We call it a vector U, U1 to UM, and it's the summation over the signal coming from all of these different users. So we have H1 times S1, H2 times S2, up to HK times SK. And this gives us also the possibility of writing this whole thing in the matrix form. We call this the capital H matrix, and we have a vector here which is our S. And this vector U is what's going through our nonlinear hardware. So say here we have U, and it goes into this nonlinear hardware. What is it that we are getting at the output? That is what we need to model properly. And in general, we can say this is an arbitrary function that takes the input and produces an output. We call it G of U, and since the hardware is placed separately at each of the antennas, and we assume that they are separated enough, the hardware will not mix the signals. It's the correlation from the signal that is impacting here. So the output from the first antenna is going to be a function only of the input from the first antenna. And it goes on like that for all of the M antennas. And there is something called the Busgang decomposition that can be used to describe the output of a nonlinear system when we have an input that is Gaussian distributed. And it can be applied to all kinds of functions that are placed here as long as we have a Gaussian input signal. And what this Busgang decomposition is saying is that the received signal at the output is going to be a scale version of the input U plus a distortion term that we call eta that has correlated elements in between each other in the vector, but it's designed to be uncorrelated of U. It's not independent because this G here is a deterministic function that is somehow distorting the signal, but we have separated out the part that is uncorrelated with U, which is not the same thing as independence. So we have G of U, and this function can then be described as having a vector U. We multiply with the matrix D, that is saying how we are scaling each of the signals, and then we are adding the eta term here. And there is a way of computing the D and eta, or at least their statistics. D is diagonal matrix, and we can compute its element in a particular way here, where it depends on the power of the signal, and it depends on the input signal here and the output signal. And everything here is conditioned on one realization of the channel. So we assume that during the time when we're modeling things, we have one realization, capital H, and then it might change later in time. And eta is a vector. It has a non-diagonal correlation matrix. We call it C eta eta. And it's what you get if you take eta times eta emission, so an outer product, we take an expected value of it given a realization of H. And this is the correlation matrix. And if it's a diagonal matrix, we have independent or at least uncorrelated elements. And if it's a non-diagonal matrix, we have correlated elements. And that is what we will have in general. Let's now create first a system model so we can look at the end performance. So we say that the received signal will be this distorted version plus some thermal noise, N. And if we apply this Busgang decomposition, we write this as D times U plus the distortion term plus the noise. And the noise is Gaussian distributed, it has a certain variance, sigma square. And the signal S that is transmitted from a particular user, say SK for user K, is also going to contain some kind of distortion potentially. So it is modeled here as having one part, which is the desired signal, sigma K, and then we have omega K, that is a distorted part. And for simplicity here, we are saying that their total power is P, and kappa is a variable that describes how much of the power that comes from each of these different parts. It's something between 0 and 1, and we have kappa times P as the power of the desired signal, and we have 1 minus kappa times P, that is the power of the transmitted distortion. And both of these are modeled as being Gaussian distributed here to focus on the base station side. Then one can compute a achievable spectral efficiency, which we abbreviate as SE, and assuming that the receiver is somehow having perfect channel state information, or CSI, then the spectral efficiency is going to be log 2 or 1 plus something that we call an SINR, signal to interference and noise ratio. And then we have an expected value in front of here with respect to this channel that might vary. And this SINR contains 5 different parts. We have a desired signal on top, which is what we are getting if we are taking the channel for user K it's the channel vector HK. We have the D matrix. So this is what we effectively is going to see here. And then we select a so-called receive combining vector, VK, which is taking the signals over these M antennas. We combine them together for this particular user. And then we have user interference. We have distortion that comes from the base station. So here, this distortion correlation matrix for eta term is showing up. And we have the distortion from the user. So this is the same type of term here, except that here we have K times P, which was the power of the desired signal. And here we have 1 minus kappa times P. This is the transmitted distortion's power. And finally, we have noise here. We have the noise variance, and we have the square norm of this receive combining vector. And what the receiver is doing is that it treats both the distortion and the noise as being thermal noise containing no information whatsoever. And we can rewrite this SINR expression as a so-called generalized Rayleigh quotient, where we notice that in all of these terms we have the receive combining vector multiplying from both the left and the right-hand side. And what is showing up here in the middle is the channel from the user, this D matrix. And down here we have the interference, we have the base station distortion, and we have distortion at the user side, and we have the noise. And since we also here have VK at the outside here, there is a way to find the optimal receive combining. It's called the distortion-aware minimum mean squared error, or DAMMC combining vector. This is something that we propose in this paper. And what this vector contains is DHK here. That is the channel that the desired channel comes through. And down here we have something that contains almost all the terms that you have in the denominator here, except this one where the distortion comes from. And irrespective if you include it or not, this vector will point in exactly the same direction. And this inverse matrix here is sort of taking the signal's direction, and we are rotating it to find the direction where we should listen to the signal and find the best balance between the strong signal and little distortion and noise and interference. So this is the optimal receive combining. It takes both the base station distortion correlation into account and interference. And we notice that it's actually unaffected by the UE distortion because this term here, the kappa, is not showing up in this expression. We will now quantify the impact of non-linearities using all this modeling framework that I presented. And let's focus on one of the components, the low noise amplifier, which is actually the one that might have the largest impact here. And this is a non-linear piece of hardware that is amplifying the signal. And we model it using a simple but well-established model, a third order, strictly memoryless nonlinear function, where the input is taken as the output minus a term here where we take the third order version of the signal. And then we have a scaling factor here that tells us how much the signal will be attenuated if you have a large input signal. And AM here can be normalized in this particular way, where A characterizes a so-called saturation level. And then we have a backoff term here that tells us how far from the saturation level we are actually operating, and we have the power of the input signal. In this way, we can select alpha to be a scaling invariant variable. And here we are showing the normalized input from 0 to 1, and then we have normalized output, so the absolute value of this one. And if we have a linear amplifier, this is just a line, the red line here. If we have a third order nonlinear amplifier, then we have two different alpha terms here, and as we make alpha larger, the curve starts to bend off more and more when we have a large input signal. And since these are not lines or straight lines anymore, but these bended curves, that is why we get nonlinear distortion, particularly when we have large input signals. So for this type of model, it's possible to compute the two things that are appearing in the Buscam decomposition, the matrix D and the correlation matrix eta. And that's something that you can find all the details in the paper. But D is essentially containing an identity matrix minus 2 times A, which is a diagonal matrix containing all of these parameters here that characterize in the hardware. And then we have an element-wide product with CUU. What is that? That is a correlation matrix of the received signal U. So we get a diagonal matrix here that we subtract, and that gives us the D matrix. And in the same way, we can use the A and C UUU matrices to compute the correlation matrix for eta in this particular way. And this is also having a particular form that you can see over here. So there are two types of distortion effects that are appearing here. One is that we're losing power and get some distortion added to it. And the other thing is that this distortion is going to be correlated. But the distortion vectors are less correlated than the received signal. And to show you that, let's say that we have a correlation coefficient that we call psi here between the input at antenna I and the input at antenna J. And we can define it in this particular way. This is the correlation coefficient definition. And this rho ij, this is just the ith element in the CUU matrix. Then if we compute the corresponding correlation coefficients between the distortion at antenna I and distortion at antenna J, after some math, you can see that we actually should take the correlation coefficient at input, we take the absolute value square of it and then multiply once again. So this operation here is saying that this could actually be a complex valued variable, so we have this sort of the third order of that one. And which also matches with the third order nonlinearity model that we're having. And since the absolute value of each of these terms is something between 0 and 1, that means that if we take this correlation term here between the distortions, then it's equal in absolute value to the absolute value of the input to the power 3. And if this is something between 0 and 1, it's going to be smaller than if we remove the exponent. So that means that the correlation that we have for the input signal is carrying over to the distortion. They are also correlated, but they are less correlated. We take the correlation coefficient to the power 3 here. The signal correlation matrix is a m by m matrix, and say that m is 200, then it's a 200 by 200 matrix. But the rank of it will be equal to the number of users, so it's usually something that has low rank compared to the number of antennas in Massive MIMO. And here we are showing some result when we have 5, 10, or 15 users. But we're not showing the signal correlation matrix. We are instead taking the correlation matrix C eta eta for the distortion terms. And we are looking at the eigenvalues. And if they had the same rank as the signal correlation matrix, then what we will see here when we are showing the eigenvalues in decaying order, and here is the value of the eigenvalue, in that case, for the signal correlation matrix, we will see something that contains 5 or 10 or 15 non-zero eigenvalues, and then everything else will be 0. That is not what we're seeing here. We see that a substantially larger number of eigenvalues are large. And as we go from 5 to 10 to 15 users, that is sort of smearing out the distortion over different spatial directions, and that is making it less influential. What if we will now neglect this distortion correlation, even if it exists? It will be more analytically tractable to deal with that. A lot of the theory that we have built up, for example, in my book Massive MIMO Networks, is built on that assumption. So what that really entails is to take this correlation matrix, C eta eta, that we computed, and then we remove the off-diagonal elements. And one way of viewing that is that we take it, and then we take the element-wise product with an identity matrix. What happens if we compute something like that instead? Let's assume that we have IID Rayleigh fading channels, so it's modeled like this. And we will compute the size of the correlation term, which was the correlation matrix, and then we multiply on the right and left-hand side of it with the receive combining vector. And to make the computations possible here in closed form, we assume that we use maximum ratio combining, where we just take the channel vector and we normalize it. And if we are using the exact expression for the distortion correlation matrix, we get this expression here, which you can compute, containing the number of users and the number of antennas. And if we are approximating away the off-diagonal elements, then we get another expression, where we can see that k plus 6, these things are showing up here, these terms are similar, and we also have a constant divided by the number of users squared. But here we also have a number of antennas that are affecting us. So what actually happens when you neglect the distortion correlation is that we are getting, or we are believing that we are getting less distortion power than we are actually having. So let's look at the ratio between these two terms, the exact term and the approximated ones. What you will then get by dividing these two expressions with each other is a 1, which is what we will get if we have exactly the same. And then we have a term, which is describing how much larger the true distortion is as compared to when we are neglecting the correlation. And we can see that this term is behaving, it's growing linearly with the number of antennas, but it goes down with the number of users squared. And that squaring effect is very important here. So when we are evaluating the effect that this distortion correlation has, we should also bear in mind that the UE device is creating distortion. And if we're taking its distortion term, then it has this form. And if we are using the same type of model as before, you can also compute an expression, and you can find the derivation in the paper. So let us simulate and see how influential this distortion correlation actually is. And we do this in the setup with 200 antennas, and we have a varying number of users, and we have some different parameter values that we are assuming. It's rather lowest now because that is what you typically get in a real system. And to not underestimate the base station distortion correlation, we assume that the base station hardware is worse than the UE hardware, so it has a larger signal to distortion power ratio. And in reality, you will probably have worse hardware quality in the UE, the user equipment, than in the base station. But we are still here overestimating how much distortion that the base station could have. And here is an example. We show the distortion over noise in decibels with respect to the number of users we're having, from 1 up to 50 users. And the red curve here is the base station distortion, the exact one, taking the correlation into account. And here we have the uncorrelated case, when we are neglecting things. And we see that there is a quite substantial gap between these curves. It's first when we are going up to, say, 30, 40 users that we are having a small gap between them. So that is sort of giving us the feeling that the distortion correlation is very important to model properly. But what is important to remember is that this is not the only factor. There's a lot of other things. In particular, there is a distortion at the user side. And that's the blue curve here. And it doesn't go down as we are adding more users into the system. So the important thing is then that when we have more than, say, 5 users in the system, this red curve have dropped down because the distortion, the extra distortion was going down with the number of users squared. And then it's the UE distortion that is the dominating factor. So eventually, we will have the user distortion, that is the main limiting factor, and also that the correlation effect will go away as we add more use into the system. But this is also focusing only on the distortion terms. What if we are looking more on the true performance, the spectral efficiency, with or without the distortion correlation? And now we will be using this distortion-aware MMSC receiver that we talked about earlier, and also the maximum ratio receiver. And here I'm showing the spectral efficiency per user, and we are varying the number of users here. And as you're adding more users into the network, you will have more interference between them. So it's quite natural that the performance will go down between these different users. That's why the trend is that we are going down. But what we can see is that if we compare these two curves here, this is with the distortion-aware MMSE, with what we believe that we get with uncorrelated distortion, and what we really get for the red curve with correlated distortion. And there is a gap here, but as soon as you have, say, 5-10 users, the gap is fairly small. And we see the same effect when we have the distortion-aware maximum ratio combining. And in this case, because the maximum ratio is not trying to suppress an interference, it drops more rapidly with the number of users as well, and then we see barely any difference here. So we can say that the distortion correlation has a negligible impact on the spectral efficiency in this Massive MIMO scenario, where we have ID rayleigh fading, equal SNRs between different users. And we can show in our journal paper a lot of other plots where we have the same type of effects. The distortion correlation have just a minor impact when we have just a few users, but as soon as we have many users, as we are expecting in the Massive MIMO system, this distortion correlation averaging out. And that is when we get accurate result, even if we neglect it. So then the question is, can hardware distortion correlation be neglected? Yes, we can do that. And in particular, when we are analyzing the uplink spectral efficiency in massive MIMO systems. And in our journal paper, we are proving this conclusion with different channel models, varying SNRs. We have quantization distortion into the system as well, doesn't make any difference. We look at the case when imperfect CSI, we look at the case when we have a large number of antennas, and we are always seeing these type of effects. If we would go beyond our modeling in that paper and talk about frequency selective fading, have various kind of compensation algorithms, then we might even see the effect that distortion correlation disappears much earlier in the when it comes to number of users. But the people that have been saying that distortion correlation is very important, they are right that you can create scenarios where it is very important to model this properly. So if you assume that you have a perfect user hardware, no distortion at all, you will see that distortion correlation plays a big role. And if you are assuming free space propagation, then it happens that the channel is pointing a particular direction and the distortion will be sort of focused in that particular direction as well. But when we have more rich channels, those type of effects is also much more quickly disappearing. So I would say that for the standard type of modeling that we do in Massive MIMO area, as we do in my book, Massive MIMO Networks, then we can use this type of models where we neglect the distortion correlation. But if you really would like to figure out the practical performance, it's important to check if it makes a difference or not to include the distortion correlation in your particular research area. So with that, I would like to thank you for listening, and if you would like to learn more, you can read our journal paper, and you can also download the simulation code for this paper from our GitHub page and rerun all the simulations and try out with your own favorite channel model and assumptions.